So in section 6, we're going to look at some applications of exponential equations, how these can be used in different situations, and how we set up equations, how we use them. So really anything that grows or decreases by a percent typically can be modeled by an exponential equation. So if you have a job and you get a 5% raise at work every year, then that would be exponential growth. If for some reason at that same job you got a 5% decrease in pay every year, that would be a exponential decay, as we call it, model, because it goes down by the same or up by the same percent every time. So first we'll look at exponential growth. So growth is when something grows by a set percent. So we can say if a quantity grows by a set percent, we'll call it R, from an initial amount, which we'll call A, then we could say the following equation is true for every exponential growth equation. So we have y equals A, 1 plus R to the x. And so y is going to be your amount, x is going to be your time. So it could be 2 years, 3 years, 4 years, 5 years, 6 years. R is that aforementioned rate, and A is the initial amount. So if I have a job where I start at $6 an hour, that's my A, and then if I get 5% raise every year, every month, then that would be my R. So we can set up growth equations and then we can use them to solve for different quantities. So for example, this says in 1985 there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% a year. So it goes up 75%, start at 285. How many subscribers were there in Centerville in 94? So if I set up my equation, I start with y equals the initial amount. Well, the initial amount was 285. So I have 285. And then the rate it goes up is 75%. So in the equation, we just always write it as a decimal. So it's 1 plus 0.75 to the x. Now y in this case is going to be the number of cell phone users, and x is going to be the years. And since it starts in 85, I'm going to call it the years after 1985. So if I add 1 and 0.75, I can really write this as 285, 1.75 to the x. So now it looks like an exponential equation we've had throughout this module. So I want to know how many subscribers there were in Centerville in 1994. Well, 94 is 9 years after 85, and years, in our case, is x. So basically what we're trying to figure out, if x equals 9, how many subscribers are there? So that'd be y equals 285, 1.75 to the 9. So if I figure this out, I just put it in Desmos or any calculator. I get 43871.98. So since it's cell phone users, we'll basically round this up to 43872. So you can see in only 9 years, this thing has gone up quite a bit. Let's look at another example. The foundation of your house has about 1,200 termites. So there's your initial value. The termites grow at a rate of 2.4 per day. How long until the number of termites doubles? Okay. So if I write my equation, y equals the initial amount. The initial amount is 1,200. 1 plus the rate. Now it's 2.4, so as a decimal, we move it over 2 places. So that's 0.024 to the x. Now remember, y is the number of termites, and x is the time. And this time is in days, because our rate is in days. So, in this case, if I simplify, y equals 1200, 1 plus 0.024, well, I can put that together, so let's not write that. Let's write 1.024 to the x. And so in this case, it wants to know how long until the termites doubles. Well, double 1200 would be 2400. So basically what we know is we know y equals 2400. So if I put that in there, 2400 equals 1200, 1.024 to the x. So when we're solving these, we want to get the exponential base by itself when you're trying to do it, solve for the variable in the exponent. So if I do that, I'll divide by 1200. So 2400 divided by 1200 is 2, equals 1.024 to the x. So now this is our classic exponential equation, which I could rewrite in log form. So if you remember, x would equal log base 1.024 of 2. And again, that's just rearranging it into a log equation. So if I put it in the calculator, it'd be x equals log 2 over log 0.1024. That's the way we did all of our log expressions before. And so log 2 divided by log 1.024 is going to be 29. So it's going to be about 29.22 to be exact, days until the termites in this basement doubles, or in the house doubles. So, bad news. Now, exponential decay is going to work very similar. Exponential decay is going to happen when a quantity decreases by a set amount. So at a rate r. So now the equation for exponential decay is very similar. Y is going to equal a, but since it's going down, instead of 1 plus, we simply do 1 minus. A to the 1 minus r to the x. And again, x is going to be our time, r is going to be our rate as a decimal, a is going to be our initial, and this is going to be our amount after whatever time has passed. So very similar to a growth, we just have subtraction instead of addition. Alright, so this says during normal breathing, about 12% of the air of the lungs is replaced after one breath. So we're replacing 12%, so it's going down by 12%. Write an exponential decay model for the amount of the original air left in the lungs if the initial amount is 500. So there's your initial amount, 500. There's your percent it's going down. We want to know how much of the original air is present after 240 breaths. So y is going to equal 500, that's our initial amount, 1 minus 0.212 to the x, and where x is going to be the number of breaths, and y is going to be the original air. So whatever it was in the lungs initially, and then we push some of the new air out, old air out, get new in. But how much of that original air is actually going to be left? So if I rewrite this, this is 1 minus 0.12 is 0.88. So we want to know how much is after 240 breaths. So that's x. So x 140. So if I plug that in, y equals 500 times 0.88 to the 240. So after this many breaths, we would think it would not be very much of the air left. So if we put that in our calculator, we get a really, really small number. My calculator reads 2.37 times 10 to the negative 11th. That is scientific notation, which is basically 0.0000000000237. Just moving this decimal point basically back 11 spots. So basically, after that many breaths, there is still some of that original air in there, but not very much at all. One of the key things about exponential decay is it can go down, it can decrease forever, but you will never get rid of all of the amount that you started with. All right, let's look about a similar equation. You drink a beverage with 120 milligrams of caffeine. Each hour, the caffeine in your system decreases by 12%. How long until you have 10 milligrams of caffeine left? Okay. So I will first write my equation. So we start with 120 milligrams of caffeine, and it goes down at 12%. So we'll say 1 minus 0.12 to the x. And then again, x is going to be the number of hours, the time, and y is going to be the amount of caffeine. So y is going to equal 120. Now this is very similar to the one above because 1 minus 0.12 is 0.88. So now what are we given in this case? How long until we have 10 milligrams of caffeine? Well, that's a y value because it's saying 10 milligrams of caffeine left to solve this problem. So I'll put a 10 in for y. And then we'll solve for x, which is the amount of time. So we get 10 equals 120.88x. So I'll divide by 120. So 10 over 120 is 1/12 equals 0.88 to the x. So again, since we're trying to solve for the exponent, we'll have to switch to log form. So this will be log base 0.88 of 1/12. So in the calculator, that would be log of 1/12, or Desmos, or however you're doing this, divided by log 0.88. So I'll just put those two values in, making sure that it is in this order, making sure the 1/12 is on top and then the 0.88 is on bottom, because that would make a difference. So I get 19.44, and that would be hours. So even after 19 hours, this caffeine, you still have 10 milligrams in your system. Our last example we're going to talk about is about money and about a concept called compound interest. Now, compound interest you may be familiar with. If you go to a bank and you put some money in your bank, then you will make interest every month or every day or whatever it is. But then what also happens as you make interest, the next month you make interest not only on your money but also on the interest you previously made. So this is called compounding, where you keep getting interest on the interest and your original money, and it keeps growing faster and faster and faster. So compound interest has a really cool formula, and the formula how to find compound interest is this. A equals P 1 plus R over N, this is an R, to the power NT. Okay? Now what do all these mean? Now A is the amount that's currently in your account. P is what's called the principal, which essentially is your initial amount, what you start with. R is your interest rate. T is the number of years. And N is what we call the number of times compounded. So if you make interest, say, every month, then N would be 12. If you make interest every year, N would be 1. If you make interest every day, N would be 365. So it's basically how often you make interest. Now most of this you can just plug this into a calculator and figure out what it is. So this says you deposit $1,600 in a bank account. So that looks like P, that's principal. Find the balance after 3 years, so that looks like T. So it looks like in all these examples, P is 1,600 and T is 3. So the first one says pays 2.5%, so R would be 0.025, compounded monthly. So that makes N equal to 12. So all I have to do now is plug all these values in. So A equals the principal, which is 1,600, times 1 plus 0.025 over 12 to the power of 12 times 3. And again, I'm just plugging all of this in to this compound interest formula up here. Now I should be able to put this all in a calculator and see what I get. So I get 17, 24, 48. So make sure you get that number in your calculator. So that's how much I have after 3 years. Okay, let's try another example. Same initial principal and time, but now we have a rate of 1.75, so 0.0175, and compounded quarterly. So there are 4 quarters in a year, 4 quarters in a dollar, same thing. So the amount in the account will be 1,600, 1 plus 0.0175 divided by 4 to the power of 4 times 3, because it was still 3 years. And again, just put this in just as you see it, and it should give you what the amount in the account is after that duration of time. So I came up with $1,686.05. So you can see, compared to the first answer, different rate, different compounding times, does a little bit different amount of money. So the last one, we have a rate of 4, and we're compounded yearly. So yearly, basically, how many times is yearly? Well, that's just 1. So the amount in this account will be 1,600, 1 plus 0.04 divided by 1 to the 1 times 3. So I'll do the same thing. So 1,600, 1 plus 0.04 divided by 1 to the power of 1 times 3 is going to give me 1799.78. So the largest of the 3 amounts, and the reason is the compounding things are different, but the biggest thing is this rate. The rate is the predominant thing that's going to help you get more money. So if you're looking at an account, you always want to get a higher rate versus getting interest more often, because it will always benefit you to get a higher rate. Okay, a couple other questions. How much money would be in the account yielding 5.3% compounded monthly if I deposit $900 in the account and left it there for 9 years? So how much can this really help you? You guys are young, so you have the advantage of actually having time to invest money. So we have a rate of R, an N of monthly, initial principal of 900, and a T of 9. So really this just plugs in just like the problems before. So you'll see how much this money can actually. So 1 plus 0.053 over 12 to the 12 times 9. So what this all turns out to be, I just plug it in the calculator. Anytime you're just finding the amount, you just plug it in the calculator. So you get 1448.59 if I round it up. So you make about $550 for just having your money in the bank for 9 years. So you get that extra money, but the problem is you don't get to touch your money for 9 years. Thus is the whole idea of investing. Let's look at one other question. So this is an interesting one. This says if we have $1,200 invested, so that's our principal, in a savings account yielding 8%, which would be a really high rate to get, compounded semi-annually, which means n is 2. How long until there's enough money in the account to buy $1 million home? So essentially we want $1 million. So this is a different kind of problem. We don't know t in this case, but we do know a. So if I remember my formula, it looks like this. So a now is $1 million. So we're going to be able to use our log and our exponential equation solving to actually figure out how long this is going to take. So I'm just putting all the values I know into the, not 12, this is semi-annually, so it's only 2. So I'm putting this into the equation, so 2 times t, which I don't know. So everything in this parenthesis I can just put into the calculator, so 1 plus 0.08 divided by 2 is going to give me 1.04. And this is the way I would solve something like this, because there are a lot of working parts. So this is going to be 1.04 to the 2t. So similar to the growth and decay we did earlier, I will divide by 1200. So 1 million divided by 12,000 is going to give me 83.3 repeating. So I'll just do 83.3 equals 1.04 to the 2t. So if I switch this to log form, the exponent 2t will go by itself. So 2t equals log base 1.04 to the 83.3. So if I convert the log to put in the calculator, I do log of 83.3 over log of 1.04. So that would say 2t equals that value. So log 83.3 divided by log of 1.04 is going to be 112.76. But the good news is, because that's a long time, we get to divide by 2, because we have this 2. So t is going to, when I divide by 2, be 56.38 years. Now, admittedly, 56.38 years is quite a long time, but if you think about it, we're growing only $12,000, so a very, very small amount, really, to $1 million in only 56 years. So if you were able to invest, say, at a child's birth, when they are 56, an investment of $12,000 in a simple account would actually grow to $1 million. All right. Well, that's all for Section 6. If you have questions, please let us know.